the dipole excitation in nuclei and resonance configuration interaction studies. So please go ahead.
Thank you very much. So thank you for inviting me to this meeting, and I will try to be in the spirit. So my title is Dipole Excitations in Nuclei in Configuration Interaction Studies, which means large-scale shell model. So as you can imagine, I cannot go very high in mass, especially if I want to study electric dipole interactions. So this is the outline of my talk, and I should underline this. My previous motivation was not really to study the pygmy modes, though I will talk a little bit about what we have in neon isotopes when such modes appear. But our previous motivation was to look to different structure effects in the low energy strengths and be able on this basis to evaluate whether the so-called Brink-Axel hypothesis holds, and as well to study the influence of the possible deviations from this hypothesis on the neutron capture rates. Okay, let's start with this reminder what I mean when we talk about the Brink-Axel hypothesis. So first of all, if you want to make applications and calculate, for example, the neutron capture rates all over the nuclear chart, what you usually have at hand as microscopic calculation is QRPA, that you all do. And those calculations are done for the ground state of the system, while in the stellar environments, what you usually need is, first of all, to you may have finite temperatures, so you have some finite temperature response, and on the other hand, you usually need to know the decay strength function. To calculate, for example, neutron capture in the Hauser-Feshbach approach. Therefore, what you assume is that your strength functions, which you can assume is that your strength functions calculated on the ground state will be the same when you go higher in excitations energy, and this is the virtue of the Brink-Axel hypothesis. So first of all, it says that your photo absorption cross-section should be independent on the initial state. And the second thing that you can do is to say that this photo absorption strength functions is the same as the photo emission strength functions, which is exactly not true. It was already indicated yesterday in the summary of the day. On the other hand, there were as well studies that were showing that when you have a pygmy resonance at low energy, it can be located near the threshold, particle threshold. So of course, it could enhance the probability of the decay by low energy gamma rates, and therefore influence the neutron capture rates, which are so important to model the R process abundances. So as said, I am in the large scale shell model framework, so I cannot go very high in mass when I study especially the E1 transitions. But some years ago, there was an experimental study in the neon isotopes, and they showed that they have some kind of strength here. I took the experimental results from this paper, and they showed that there is some kind of low energy enhanced strength around 8 MeV. And we did the shell model calculations back in the time quickly, and we saw that we have such a structure at low energy around 8 at 10 MeV. And the experimental sum strength is given here, and they say, as you can see, it is more or less 5% of the TRK sum rule, and this was as well reasonably reproduced in the shell model. So in addition, there was as well a study from QRPA, from Marco Martini, Sophie Peru, and Marc Dupuis, that was published in this paper, and I will refer a lot to these calculations because they are published and I have them in hand. I'm sorry if I don't quote some other QRPA calculations that could have been done in this mass region. So to me, it looks like a perfect background to check different effects, to study evolution of the photo absorption strength with energy or spin. So to answer about the Brink-Axel hypothesis, and in addition, we have this possible pygmy strength that we can as well follow how it behaves when we move in mass, but as well when we move with neutron number, but we move as well with excitation energy. So this is the framework I use to make calculations. So in the shell model, if you want to describe the E1 transitions, you have to have the full complete one, what we call 1H per mega model space. which means that, for example, for neon isotopes, which are nuclei with particles in the SD shell, valence particles, you need to consider free oscillator shells. So we will make the excitations from the core will be helium-4, then we will make excitations from 0p to 1sd, and then from 1sd to 1pf. So these are small nuclei, and so this blue arrow shows you what is the one particle Hall excitation typically, and we will take all of them into the account, of course, and make a diagonalization. On the other hand, since it is quite light systems, we can also test on the free h-bar omega calculations. So in addition to this one particle, one Hall, I can also add more excitations to have the free h-bar omega calculations. These are more tricky, but they can be done. So the interaction that I use is empirical one, and there is plenty of fitted parameters in the interaction. So to reproduce exactly the spectroscopy of the SD shell nuclei, and these interactions that I use there were as well adjusted to reproduce very well the negative parity states of the SD shell nuclei, and they were used to study the E3 transitions with a quite good success. So in some pictures, I will show, of course, the strength that are smoothed with some Lorentzian, and I will tell you more about the method that I use to calculate the strength functions. Let me just show you one more thing, because I will not discuss in detail all the free h-bar omega results for the simple reason that the interaction was not adjusted to free h-bar omega calculations. So of course, if you adjust on one particle Hall level, when you make free h-bar calculations, the position of different states is moving and it's not reproducing experiments so well. But I show you these curves just to indicate that there are basically two effects that you have to remember. So the first thing is that when we have a larger calculation, usually it suppresses a little bit the strength. This is one thing. On the other hand, if you look to the distributions, they are preserved. So in general, what I will conclude on in this talk, it does not really depend on the configuration space. So whether it is large calculations, smaller calculations, the basic effects stay the same. And as you can see, the strength is, maybe you don't see it at large distance, but the strength is basically a little bit shifted, but these peaks are more or less the same, whatever the calculation is. So a few words on how I calculate the distributions, because the advantage of calculating the photoabsorption shell model is that it can be done in a computationally cheap manner with the so-called Lanczos strength function method. So what we do is, in fact, you can just apply the operator of your interest on the initial state of interest, which can be ground state, but as well excited state. And you calculate what you call a sum rule, and then you can just use this sum rule state as a pivot for starting the Lanczos diagonalization procedure, and this will give you the strength distribution. So advantage of this method is that it gives you the distributions in the whole energy range that is covered by that is covered in the given configuration space. Oh, sorry. Somehow I changed the slide without touching the computer. So some of this works. Okay. So yeah, you can cover the whole energy range using this procedure. So if you calculate just one iteration, you will have one state here in the middle, which will be the sum rule. Then if you pursue the iterations, you will recover more and more details of these distributions. So in other words, if you make as many iterations as you have a dimension of your system, at the end, you will have, for example, in this example, the matrix is something like around 10,000. So if you make the same number of iterations, you will converge all the states. But this is not necessary generally to have a distribution shape, because if you fold it with Gaussian, for example, that you see that the results looks exactly the same. So this is the advantage. You don't have to diagonalize the huge matrix. It's enough to make a finite number of iterations to recover your distribution. On the other hand, you have to remember that these states sometimes are not physical states. This is something we call doorway states. So it's not yet the converged states, but when you have major peaks, you know it quickly after some number of iterations, which is in my case, will be something like 300, and it's perfectly adapted for this type of studies. Okay, so each time I present this calculation, somebody asks me, what do you do about the center of mass? So I prepared my answer. And what do we do about the center of mass? I always have this question. Yeah. So what we do about the center of mass is the old trick of Lawson and Glockner. So this means that instead of diagonalizing the shell model Hamiltonian, you diagonalize this operator, which is a shell model Hamiltonian plus center of mass Hamiltonian with a coefficient. So this coefficient in my case is something like 10, and the idea is to push the center of mass eigenvalues to energies that are not of interest for you, so high energies, and a priori it should be as well prevent the coupling of the center of mass states to the physical states. And this is the proof of principle picture. So first of all, what I usually do practically is that I calculate like 300 iterations. I keep the states that have the largest overlaps with some rule state. And then I just compute the mean value of the center of mass Hamiltonian in the states to check that they are not spurious. And doing that, for example, you have a 22 neon, you find the values that are very, very small, I would say, at the level of numerical precision. So I consider that I have a spuriosity less than a fractional part of a percent. So this is not an issue. So on the other hand, I did here a calculation for educational purposes. When I did 100 Lanczos iterations, I saved all the states, and this is what you take, what you get as the B1 distribution with this 100 iteration in neon 22. So the units here are arbitrary, so to show you both on the same picture, I multiply their scales anyhow. And here, this red peaks on the negative scale is the center of mass eigenvalues. And you see that they appear at energy that is no longer considered, no longer covered by the distributions that we will study. So we don't have a spuriosity, any spuriosity below the, let's say, 50 MeV, where the BA1 distributions are considered. And especially myself, I will be really interested in the low energy around, let's say, up to 15 MeV. Okay, so this is what we get when we study the neon isotopes. Starting with n equals z neon 20, when you see that you have nothing at below 15, let's say 15 MeV. Then when you add neutrons, some low energy appears up to this case that we saw already neon 26. And I pursued the calculations up to neon 28. Afterwards, it's tricky because you go to the so-called island of inversion region when the deformed intruder configuration dominate the ground state. So the physics is a bit different. Therefore, I stop at neon 28. And here you can see the comparison of the QRPA calculations I was citing to the summed shell model strength of the 1 h bar omega level. So this was a sum done like in the paper of QRPA, it was up to 14 MeV, and you can see that both calculations give the same trend. You have more strength at low energy, though shell model is giving you much more strength at the low energy. And here I have as well the comparison of this typical QRPA calculation and shell model calculation. So this QRPA, as said, this was with Goni forces. And yeah, if you just plot the, if you just plot the peaks like this, so what you can see is basically that the summed strength up to 50 MeV is larger in the shell model than in the QRPA, and then we have much more strength at low energy. I have as well a detailed contributions from the lowest peaks, because in fact, I don't know what I calculate. So to go back to the discussions of this metrics, I don't know if it's low energy dipole response, or if it is a pygmy mode, or how should I define it? But if I look to the low energy peaks, what I can tell you is that majority of these peaks is of the neutron nature. So there's only one that is coming more from about 50-50 protons or neutrons. The rest is of neutron nature. Then if I compare, for example, the first peak to the QRPA calculation, my peak is much less a single particle. For this first one, I would qualify here at 4.6 MeV, I would qualify it at more single particle transitions. And then if I look to my higher peaks, so this around from 8 to 10 MeV, let's say, what I see is a very, very fragmented wave functions. So there are no components, dominating components in terms of particle Hall spherical configurations that would dominate my wave function. And if it was for quadruple correlation, I would consider that my nucleus is collective deformed. This is how in my language, how I define. So here I would say that there is some collectivity in this low energy peaks. Okay, just for comparison, the first peak, it's in QRPA, it's over 10 MeV. It contains 70% of this first contribution that we observe also in shell model. Of course, this contribution from S1 to P3 is appearing a lot in this low energy range. Okay, so this is to show you that, of course, we can as well calculate the odd mass nuclei, and the behavior is more or less the same. You add neutrons, you produce some energy, some dipole strength at lowest energy. So I will not discuss a lot of odd nuclei, maybe one case just to show you how it behaves in comparison to the even one in the context that is interesting for me. Okay. So since we are looking to prove or invalidate the Brink-Axel hypothesis, I want to refer to some previous studies that are on this subject in the literature. And the first one is the paper of Calvin Johnson from 2015, when what he did was large-scale shell model calculations, but he studied only the sum rules of different operators. And he studied the behavior of the sum rules as a function of excitation energy. And you can see here the results in light nuclei. So he goes high in energy up to sometimes even 120 MeV. And what he concludes for the E1 dipole response is that this is rather flat. So he concludes that the Brink-Axel hypothesis is conserved. Though you can see that there is some fluctuations on this curve, though in my opinion, they go from the fact that he kind of reduced his model space, and this behavior comes even more flat if you, in larger model space, you take one H bar omega full model space. You see here the calculations. I didn't go as much high in mass, but you can see that up to 25 MeV, these red points show you the sum rules are perfectly flat. So the behavior is flat. So we can also say that there is no violation of Brink-Axel hypothesis when you look to this sum rule of the operator. On the other hand, you have as well here the green points that are M1 dipole sum rules, and those move a lot. Those do not have this nice flat behavior. And this is as well in agreement with the previous calculations by Calvin Johnson when he decomposed M1 to isoscalar isovector parts. But anyhow, in both parts, you see that when you move in energy, there is some strong variation of the sum rule. So this is as well observed here. So this agreement between different studies is quite good, and it indicates that the Brink-Axel hypothesis for M1 transitions but there is some deviation already when you look to the sum rules of the operator. Okay, but the sum rule is not all, and in fact, to say a little bit more about this behavior of hypothesis at low energy, I mean, generally, I did as well the detailed calculations of photoabsorption strength for different initial states. So the first case I wanted to discuss was neon 22. So the prediction from QRPA was that this one is the most deformed among the neon chain. So they predicted something like beta 0.5 deformation. And if you make a Hartree-Fock calculation with USDB interaction, you get more or less the same deformation, beta 0.49. So you know that in deformed nuclei, you can have some split of giant dipole resonance. In fact, in my calculation, so the ground state is this black curve, and you can see as well that this is some kind of double peak structure that seems, however, to disappear when you go up in energy. So here you have different initial states, it's always 0+, but you see in the parentheses where energies in MeV. When you go higher up, your profile in fact is changing. So here I give you the energy of the first peak in all these calculations, the centroid width, and this is the summed strength to 10 MeV. So the sum rule up to 10 MeV and the energy weighted sum rule up to 10 MeV. And you can see that there is already some, so while the centroids and widths are similar, and you could say on this basis that the Briggs-Axel hypothesis holds for the GDR, then the details, especially at low energy, are quite different. And this is unfortunately these details that are interesting when you are making the neutron capture calculations. So when you take such a nucleus like neon 22, what you see is that you have less strength on the ground state, more strength on the excited states. And this comes from the simple fact that when you go high in excitations, you have more excited states. You don't have this large gap in the spectra of nucleus. So your first peak energy will go down when you go higher up in energy. So this is the simple result of that. Now, if you go to a more neutron-rich nucleus, which has some kind of low energy bump, let's call it pygmy, then the effects are not so obvious. So there is as well the first peak, the first peak goes indeed down because of the same effect of availability of many excited states of different parities. But on the other hand, if you look to the energy weighted sum rule up to 10 MeV, this is the largest for the ground state, which comes from the fact that there is this bump here at 8 MeV, which seems to be absent when you go higher up in excitations. But well, anyhow, we can see as well that the centroids and widths, in spite of everything, are quite similar. So let's say for a moment that the Briggs-Axel hypothesis holds for the giant dipole. And now let's look a little bit more in detail for this strength distributions at the lowest energies. And here I compare to this nice picture from Elena. So this is not the same nucleus and different type of calculation, but this is very interesting. And I would be very much interested to see such calculations in the neon isotopes with temperature, when you can really recover or see the same effects in both, which is of course, but if you look to the ground state, there is this no low gamma strength due to the gap, while some low energy strength appears when you go up in excitation energy. So here I put temperature, which is really, really roughly estimated. I didn't find good parameters for this nucleus, but okay, let's say if you go up in temperature, then you can have this low energy strength. While in calculations of Elena, you see the same effect, but there is no strength when you consider the ground state, and then with temperature, there's some bump here that appears and fills this gap between 0 and some higher gamma energy. So both calculations show you that there is some deviation of Briggs-Axel hypothesis, and this deviation is the largest for the ground state of the system. Okay, so now just for a comparison, there is neon 27. This is an odd one. So a priori in the odd even nuclei, you are not necessarily having this gaps in energy spectra. The states can be closer. And here you see as well that the first peak is much lower. The effects, however, are more or less the same. So the energy of a peak, the first peak goes down when you go up with the excitation energy of your initial state. And then, yeah, here the sum rule again is quite larger for the ground state because of this bump here, though it's not, the effects are not so pronounced as in neon 26, but I would say that generally the odd nucleus has more or less the same behavior. And the same behavior, there is one thing that is interesting for me, and I don't, if I can say that I don't completely understand yet, is that this bump is only present when you look to the ground state. So I don't see something equivalent to pygmy when I consider the excited state strength functions. And I was trying to understand this effect. And here I will show you two nuclei, neon 26 and neon 28, and try to analyze a little bit in detail, let's say, what I can get when I calculate and compare these two things. So this is important because, we said that the photoabsorption strength function should not depend on the structure of initial state, but this calculation shows you clearly that it is dependent on the structure of the initial state, because I don't see the other reason on what it could be dependent. The 1- state that I calculate are the same in both cases. So this is neon 26, and you see the gamma strength in black, it's for the ground state. In red, it's for the excited state. So you see the similar behavior in both nuclei that have this low energy strength here between 8 and 10. So I put here as well the maximum transitions that is observed in this energy range, and this is for gamma energy. So you see that there is a difference of about a factor of 2 between the largest peaks in ground state and in excited state, so between this black and red curves. So clearly there is some redistribution of a low energy strength that depends on the initial state structure. But now how this redistribution is, why this redistribution is getting place, this is more tricky. And to understand that, we have to look what these states are. So in neon 26, it's a nucleus that have 2 particles in S1/2 orbit. And as I said before, I mean, these states in shell model, I mean, in these calculations, they are never very pure. So if you look to the ground state, for example, you have that this configuration with these 2 particles in S1/2 orbital is only 53%. So this is not so much, but still it is a dominant component. And of course, you can only create 1 0+ in the S1/2 orbit. So then if you want to make another 0+, you have to change the configuration. And it appears that in this nucleus, you can promote the 2 particles to d3 level. And this will be your configuration of the first excited 0,2+ state. But again, these are not very pure states. It's only 33%. So now, this picture shows you the strength, which is between 0 and 10 MeV in excitation energy. In excitation energy, what it means? That the first excited state, the one that I show here, is located at 429, and the first 1- states is at 464. This means that a priori, when I excite this state, I should have transitions to the same, to all of the 1- states in the system, the same states that I have here. But as you can see, the results, there is nothing. It's empty as, I don't know, beach in Malaysia, let's say. So there is all these big peaks disappear when I construct my strength functions on a different state. So there is a big sensitivity to the structure of the initial state in this case. I will say that it is in this case because I don't have a proof that it will happen everywhere, no matter what is the initial wave function. Trying to understand that, I plot you as well here the contributions from different matrix elements. So the calculations are done. No, I don't have, maybe you have better idea or suggestion how it could be understood. What I have done is just to plot the contributions from different matrix elements. So you have here excitations from 1p to S1/2, or from 2S1/2 to PF shell in this first panel as blue and red, and then the other contributions from 1p to the D shells, or from D shells to the PF shell are given here in the lower panel in different colors. And of course, you can as well notice that I changed the scale so you can see something, but sorry, I'm still playing wrong with this pointer. But okay, you can see that in both cases, it seems that we have contributions from nearly all matrix elements. Of course, the final peaks are not really one matrix element contributing, but there are very many interferences between them and not necessarily constructive. But anyhow, here you have more or less the same contributions from the same matrix elements, but okay, no, there is no matrix elements that would be really missing or dominating in one case with respect to the other. Oh, sorry, because I changed again to another nucleus. Okay, I was on this slide, sorry. So there is only one matrix element that appears more for the excited states than for the ground state. And this is, of course, from the D3 half, because this shell is occupied here. Okay, so just to make it more general, there is another case, which is this neon 28. And when you observe exactly the same behavior, though the structure of the initial state changes again. So here the first 0 plus is more pure. This is quite pure state, 78% of S1 half, D3 half, both two particles. When you go to the first excited states, it's still based on the same configuration, but less pure, 30%, and all the other contributions are less significant, 30%. So you have the states that are built more or less on the same configurations with different percentage, but you still observe the same behavior. Your pygmy disappears when you consider a different state. So there is here peanuts, and again the analysis of the matrix elements shows that they are all present, contributing somehow, but not resulting in the same final magnitude of BE1 transition. So my understanding is for the moment of this different type of effects that I see in the strength functions is that more mixing you have in the initial state, less, how much do you have? 10, okay, that's great. So my understanding is that the more mixing you have in the states in which you start, less of this low energy strength you have, or the pygmy type strength you have in your response function. Okay, but this is the open question: what will happen if we move to other nuclei? This is only one particular case of light nuclei, so this could be checked somewhere else. So the last part of my talk is the second aspect of the Brink-Axel hypothesis, because as we said, if we take a QRPA strength function and we want to calculate the neutron capture, then we have to assume that the photoemission and photoabsorption strength functions are the same. And we know that it is not true, and it was as well shown. I mean, the shell model gives you this possibility to state that this is indeed not true. And this is shown in this panel where there is calculation in scandium 44. So you see it's a PF shell nucleus, and it is odd-odd with a 2+ ground state. And this is the response of the ground state. You see blue, so some kind of giant resonance. Then you have here a different strength that was calculated a completely different way, much more complicated than the photo absorption. So what I did is just what generally in shell model can be done, is just to calculate a huge number of low energy states below the neutron threshold, and then define your strength function in this way. So you just take averages of the strength per energy interval as your probability distribution, and you fold it with a level density to obtain the strength functions. And you see that this procedure gives you something quite different. So you start with you calculate all the states to some, let's say 10 MeV excitation energy, and you average the transitions from them. So you create some low energy limit to these strength functions. And in this paper, but I have to underline that the starting calculations were done in the axially deformed Goni QRPA approach for the whole nuclear chart. And so this was the basis for further, let's say, the database for calculations for applications. And so the whole nuclear chart was calculated in the microscopic approach, but then to account for these different low energy effects in the decay strength functions, a number of effects was added empirically. So, for example, there was empirical formula to, let's say, mock up these effects of the decay of the low energy levels that produce the tails in the low energy gamma range. And as well, there was the famous upband added that due to the shell model calculations come from the M1 transition. So you see here the examples calculated in xenon and barium. This is how the QRPA strength functions looks like when you add the upband calculated from the shell model and you try to make a general formula to reproduce the two of them. And this was done in this way in this paper, and this is what you get to, for example, in the Talis code, if you want to make calculations of the neutron capture rates. Okay, and here I compare how this empirical formula can reproduce the results that I obtained with microscopic shell model strength functions. So each you have here the E1 strength calculated in shell model in different ways. So you have photoabsorption on different initial state. Then I added the decay from the shell model, which is exactly calculating these levels up to the neutron energy separation energy, which is given here by the vertical bar. And then I plug it, I do the same thing for the M1, and then I plug it to the Talis code, and I calculate the impact of changing of the strength functions on the neutron capture. And you can see it, see the result here. It's compared to the results using this QRPI empirically modified strength functions, and you cannot see them really because they overlap with the shell model results for the ground state. On the other hand, if you calculate the real decay of the nucleus in the shell model, you get something that is quite higher with respect to the other strength functions. This is for neon 22, sorry, to neon 21 target. But if we go to more neutron rich, it changes even, it changes differently, let's say. So here you can see as well the strength functions calculated for different initial states in shell model, the decay in the shell model, and there are two QRPI calculations. So one is, let's say, raw calculation without any empirical treatment, and the other is with this empirical addition of the corrections, different corrections to reproduce better the low energy strengths. And so you can see here the E1, M1, you see this empirical upband here in the gray strength that was added, and how it impacts the calculations of neutron capture. So if you go to a neutron-rich nucleus and you make like the raw QRPA strength functions, it gives you very low cross-section for the simple reason that you see here that there is no strength below 10 MeV. So of course you cannot get any agreement with experiment or other calculations. On the other hand, if you make this empirical corrections, it falls reasonably in between other shell model calculations. And you can see that in this example, the shell model decay is not that large that in neon 22. And this comes from the fact as well that this neutron cross sections is very low. So you don't have many states around the neutron threshold, and it does not produce so much of the low energy strength as it was the case in neon 22. Okay, so this is, I think, the summary of my talk. So my conclusions would be that the Brink-Axel hypothesis, to my taste, holds for giant resonances, but in low energy regime, we have real problem. And so what I am bothered with or puzzled, let's say, is that to me, the pygmy dipole looks like something that I can have only in the ground state distribution. And of course, when we look to photoabsorption and photoemission, it's not exactly the same thing. This is what we know, but it is really well, let's say, proved in the shell model calculations. And what type of strength you take for the calculations of the neutron capture, it really has a sizable effect. So of course we have to continue that, and we continue that to benchmark the QRPA models and other models of decay that can be used. And I want to thank especially to my late colleague Etienne Corrier, that was behind all the shell model codes, as you know, and as well in this case, he was as well the guy who did this nice empirical interactions for the opposite parity states in the SD shell. Okay, and with this, I thank you for your attention.
Yes. So thank you very much. Are there questions from home, let's say? It doesn't look like. Are there questions from the audience? Yeah. Okay. So then first, Niels.
So you showed the evolution of dipole transition strength in neon isotopes, and then you showed these matrix elements. Are these matrix elements all neutron matrix elements,
No,
or proton, or you cannot distinguish?
Neutron. I sum proton and neutron. Yeah. So I mean, if I would like to plot all of them, it would be maybe two. So it was mixed proton and neutron contributions.
So thank you for the nice talk, Camilla. I have many questions, but probably we can discuss after it.
No,
well, I can give some short questions now. Okay. What are the shell model parameters? Do you use any effective charges? Did you try to compare with giant dipole resonance data? How well you can reproduce widths, centroids, and so on? I mean,
so this is a major problem. Is that okay? So shell model parameters for effective charges. So we use always the same effective charges when we calculate the E1 transitions, which are both when you have extracted the correction for the center of mass. But these are always the same for, I mean, it's calculated for each nucleus in function of this mass, but it's there are no more effective charges than that. Now, the interaction is the same for all the nuclei, so I don't fiddle with any more parameters.
And what kind of interaction do you use?
So this is the interaction that is mentioned here. So, you know, it's a typical shell model interaction like USDB, which is, by the way, the interaction that is inside. So you fix it once forever to reproduce all the spectroscopy that you can, and you just leave it. So you don't adjust anything to E1 transitions particularly.
Yes.
But now, what was the next type? You said something that I wanted to address. Width. Okay.
Yes,
so now the giant resonance. This is the problem, because as far as I know, I'm not sure that I have some parameters in this nuclei. And then I cannot go to the nuclei when it is known.
But I mean, do your calculations approximately exhaust the sum rule?
No, they overshoot the sum rule. They overshoot from that should be the case, and this I checked that they overshoot the sum rule. But then, for example, if you take from the tallies the empirically modified the strength functions to reproduce the GDR position, then of course it's as well empirical modification. But if you compare the modified with mine in neon, it looks better than the simple QRPA. I don't know if it proves something that the global modification of the GDR parameters leaves something more close to shell model. But yeah, this is unfortunate. Then I don't know about light nuclei, probably when there is some data about GDR and I could check, and I didn't think of that. Yeah, so you can tell me which ones and I will check.
Very little, actually.
Yeah. Because I don't know if there is more hope that I will one day calculate, I don't know, nickel 68, or there is more hope that you can calculate neon isotopes, and so we can compare.
Yeah. Also, concerning the interpretation of your, let's say, pygmy strand.
Yeah.
Did you try to calculate transition densities to see transition densities for this peak, which you don't know how to interpret?
I'm not sure that we are talking about the same transition densities. What do you mean by transition density?
I think you have radio
Yes,
yeah,
radio transition densities. Yes,
this is I cannot calculate.
You cannot calculate.
Yeah, but I cannot calculate. This is a problem. Yes, but yeah, okay. This is something yes, but it's in oscillator basis.
Yes, configuration amplitudes left.
Yes, and then I can this I can look at. Yeah, you are right. Yeah.
So could you show the comparison of your 1H bar omega and 3H bar omega for sum rule and total strength?
Yes.
So if I saw correctly, the strength which you got in larger space is smaller,
Yes, it's
right?
smaller,
For
yeah.
E1.
Yeah.
So is my understanding correct that this is the effect of ground state correlations when you enlarge the space?
Yeah.
Because in QRPA is the vice versa. When you enlarge the space, usually you get more strength. So my suspicion is that it's just basically the effect of the ground state, two particle, two hole effects on the ground state. Is it that or not?
My understanding of that is that I mix some intruder configuration to the ground state when I enlarge the space.
Okay.
And this suppresses the E1 strength. So it would be like
Yeah.
the same effect as I see on the excited states. In
And
fact.
just note about loss on prescription. It is valid if you include really complete 1H bar omega plus 3H bar omega space. Okay, so it just note.
Yes, but okay, but the proof of, I mean, it works.
Okay.
Okay, so let me, I think Stefan, it's time of Stefan, if I'm not mistaken. Please,
Oh, no.
Stefan, ask your question.
Yeah, thank you, and hello everybody. Just a question, Camila, on the neon 26 low energy strength that you showed for the for both for the photoabsorption and for the decay. You don't have a zero limit as you used to have in other nuclei for the M1 I'm talking about, and the same goes also that
This
and
one.
yeah. So this one you don't seem to have a non-zero limit at zero gamma energy, as you used to have before, as you showed also in the xenon and barium case.
Okay,
How comes?
no, this is no, this is just a question of you know, it's folded, and this is just a question of this folding. If you, because if you make, I mean, there is never zero limit. It's always 0 at 0. It's just a question of graphical representation.
And just
So it depends whether case you talk about there was a 0.2 point gamma bin. So of course you have something in 0.2 gamma bin. In this nuclei, not, because you don't have this small gamma rays. Yeah, this small gamma you don't have.
And the case that you showed for xenon and barium, I don't remember if it was a photoabsorption. It was a decay actually.
This one?
Yeah.
No, this is the decay. This is the decay.
Okay, so you still have the same. So the same applies still. I mean, nothing changed for xenon and barium.
No, nothing changed, Stefan. No, don't worry.
Okay, that's good. Because the question of to what extent you can extrapolate your results of neon to other charged nuclei, somehow you have the response here with the xenon and barium.
But you know that you can extrapolate. Extrapolation will not be the same in all nuclei. Here you have completely different heavy systems, and here you have systems when you are at 1.5 sometimes neutron separation energy. So of course you won't have the same effects exactly because you have much less states.
Yeah, exactly.
Here you have, okay, so for example, neon 22, I don't remember how many states there are, but there are many. But in this guy, up to 5 MeV, you have something like 15 states. So you won't have the same strong effects as you have in barium or in xenon.
Okay, that's thank you.
Over here, Cami.
Thank you.
So regarding two of your statements, it's on this slide, and it was also on your summary slide, because it's very interesting. And it's also interesting that Stefan basically was the one asking a question before me, because here you say, all right, the PDR does have no influence on the neutron capture cross-section.
I forgot to make the
yes,
statement.
and then on your last slide, you basically claim, at least in the Shah model, the PDR only appears to be present built on the ground state. So if that is true, and I am not aware that anyone, so if that is true,
yeah,
that it is only part of the ground state gamma ray strength function, and I'm not sure whether any other theory has looked at that yet, at that branching, and looked whether the PDR bump really appears on each other state. When that is true, does that in all cases mean, and maybe Stefan can answer that too, that it doesn't influence the N-gamma cross-sections in statistical model approaches?
Okay, so let me just answer this one. What I wrote here was about this case, but the PDR has no influence because here, as you can see, the threshold is at 5.5, while the PDR starts at something like 8. So this was the comment on this case that I forgot to mention. But on the other hand, yes, you are right. But if we don't see the PDR on excited states, and if we don't see any of that in the decay, then it doesn't play a role for the neutron capture. Yes, but this is what they say. So you can lapidate me. But there is a question
but Elena, do we know that?
But can we know that?
Can you look at that? I mean, I know that in your model, you looked at the coupling now, or you can calculate decays down to the first 2 plus. I know that Nadja can do that now. So in principle, you could look at the E1s. You do.
Yeah.
Okay, I think this is very important to figure out, because when when these things are put out there now, funny, right? No? I mean, it kind of like questions the field and our motivation, right?
I think the reason is that there are just a little amount of space,
We would be interested in the answer, Elena. Could you use the microphone?
Yes, sorry, it was kind of my fault as well.
Thank you.
Okay. So.
No, I don't have concrete results, but just based on the intuition and on the Nadja's calculation, I would say this is probably the situation which pertains to light nuclei, because this first excited state, also the second, they are relatively high in energy, while in heavy nuclei we have very low line,
so
2 pluses.
The best thing to do would be to calculate this one and another one and see.
Yes, we need more calculation. Thank you.
So wait a second. Let's see.
Okay.
I just want to make a comment, but already.
Your comment, please.
So just a comment. I did calculations of iron 56, and I really see pygmy dipole resonance built on excited states. So
okay,
but probably I have just one case.
Yeah. So I mean, from me, I can do this. I can do any other light nucleus. Maybe I can look to the proton pygmy if it behaves the same thing. I don't know if it can be useful. But I'm limited. You have to help me.
Yeah, a little bit more to basically the same question, because I mean, that's an interesting observation. I mean, empirically, or if you look at the experimental data, which, as you said, there's hardly anything in these light neutron-rich nuclei or nothing. But in heavy nuclei, what you see is empirically, you see something like a pygmy resonance, whatever the structure in the decay. I mean, if you look at the Oslo data, it's always there to some extent. Elena's point was that this may be related to level density and the energy of the first excited state. That makes some sense. But now I started wondering, I mean, even in the heavy nuclei, there are data on, let's say, spherical vibrational nuclei, where maybe the first excited states at something like 2 MeV, and then you have the odd neighbors where the first excited states can be very low. And as far as I know, I mean, there have been studies of isotopic chains, many in the Oslo case. You don't see any difference in these properties.
Okay.
Thank you very much. Are there more questions? No? Okay, so, just one last question.
Yes. Yeah, I thank you very much for your talk. And I think it was very good to see the power of the shell model.
Yeah, the power is limited anyhow.
This kind of calculations. So yeah, it was great to see the comparison with our continuum final temperature case. And I think this single particle continuum, we could do can be really predictive in this energy region. And I would like indeed to have the same nucleus then, but unfortunately the very concept is purely statistical, and we need some considerable level density to define the temperature. So maybe we can find a point somewhere in
maybe
to
in DF
to check that.
But,
Yes,
but when it's very Newton rich, it can be tricky as well. But okay, I will try to enhance my since it is photo absorption should be easier in shell model even for heavier ones.
Yeah, I think we really need to push this temperature continuum. Yes. So I just wanted to ask one question. Maybe in the end, when you calculate this giant resonances, the large energy, the strength distribution up to high energy, do you play with your configuration complexity? Because this is a very pivotal question for us. Like we can, for example, cover the large energy range with very simple configurations, but then we can add on top of that, like 2 particle 2 hole, 3 particle 3 hole, and so on.
I don't change anything. I mean,
do you have it fixed? Like you have the full configuration?
It's always the same configuration for the whole range of states that I calculate. I mean, it's the same configuration space.
And what is that?
So now I showed you for the low ones in the beginning that it was very mixed. On the other hand, I don't have this. I don't have this for resonance, for example. I don't have them. I can have them, but I don't have them now.
But how about this particular one?
So this is what this tells you that it's very spread. So the wave functions I don't even print it because it contains 1,000 of components of 1% of something, of some configuration. It's very mixed.
But how many particle hole configurations do you have in the wave function? Can you tell?
Okay, but this is as well difference with you because how do I mean, there is one particle, one hole with change of parity, but there is as well all the mixture of the SD shells.
Yes. So you have all of them.
Yes, because the SD shell is like, I mean, the starting point is the whole configuration mixing in the SD shell. So if I would have to count them with respect to the lowest configuration or something like this, so this is not obvious coming from one basis to another to compare.
I see. It's like and you have to change the interaction also.
No, interaction maybe not, but I mean, if you make full configuration mixing in the SD shell, it's already more than you know, than one particle, one hole, or whatever. It's you have all the correlations already inside, and on top of that, you add one particle. You have a set consistent basis. Yes. Yeah, you would have to. In fact, you would have to go to the spherical basis to compare with me, probably.
I am in a spherical basis.
You are in a spherical.
But you have a set consistent basis.
Yes.
Yes.
Okay, I see.
This was done by some people to compare. Yes, there is a paper with Thomas Rodriguez when they compared, you know, he came back to the oscillator basis and they compared the occupations, how it looks in both, because otherwise it's not comparable. This is the problem. So I'm not sure, for example, the 67% here means the same thing that my 27. I'm not sure that it means something, you know, because I start with something more mixed already.
Okay, but for transition densities, I think we can compare because I remember comparing with Alex Brown.
Yes.
And this we did for Gamov-Teller. So I think we can also do it in this case, but we just have to transform them, this matrix elements to the R space, to the coordinate space.
Okay, this I will think it over as well. And thank you very much. I think
thank
we have to finish.
Thank you for all the questions. Thank you very much for your talk. So let's thank Camila again.